Happy Monday, everyone. I hope you had a beautiful weekend. It was beautiful outside. I hope you enjoyed the sunshine. So remember, you have remote days, Monday and Tuesday. You will not be at school. So this video will just be going through your graphing packet that Ms. Wallace gave you on Friday. This is the entire video. You can fast forward through this video to the sections that you need or just to check your answers. However you need to use this video. It is not locked where you can't just go through it. I've made it so that you can use the video whatever works best for you. So a lot of the stuff we're going to be looking at in the graphing ties directly with math and science, what we've been learning in math and how it correlates to what you've learned in science already this year. So obviously we know that line graphs compare two variables and each variable is plotted on an axis. A line graph has a vertical and a horizontal axis. Our horizontal is the x-axis and our vertical is our y-axis. So that's the introductory section. So then it says line graphs are important in science for several reasons. They show specific values of data. It can show trends and relationships, which is really also important in math. That's going to be really important on when you do take the Aspire test, that's what you're looking for is those trends and relationships and how things increase or decrease. Also allowing the viewer to make predictions, that's important, when recording within recorded data. So within means within the data that's given to you, and that's called interpolation. So inter means like inside the data. Or we can make predictions about the data that's not recorded, so that's extrapolation. So if you think of it extra, it's not on the graph, it's extra. So if I look at this, determine which of the values below is interpolation and which is extrapolation, explain why. It says the value of Sarah's car in 2004 was $17,500. So that would be an interpolation because it's in the current data. The value of Sarah's car in 2008 would be extra, which I know both of these would be inter now because these dates are like super old. So that tells you how old this paper is too. But sometimes oldies are good. Okay, so let's move on. Okay, so just like we did last week in math class, when the first thing you need to do is identify your independent and dependent to make sure that you're labeling correctly, and you can read back through the top up here as we're going through if you need to. But let's look at the example practice problems. It says a student wanted to observe how changing the temperature of the aquarium water would affect the breathing of the goldfish. So a great way to think about independent versus dependent is which one is causing the change. So changing temperature is affecting the breathing rate. So this one is independent because it's the one that's affecting something. So temperature would be your independent variable. And your dependent variable would be the breathing rate of the goldfish. Okay, a student wanted to determine how tall corn would grow if different types of fertilizer were used. So what is the thing that the student is changing? The student's changing the fertilizer. So the fertilizer is your independent, and that whatever fertilizer is used is going to tell us how tall the corn is going to grow. So I'm going to put height of corn. So those would be your independent and dependent. So real quick, remember when you're graphing, you got to determine a scale. Pick a numeric value that makes sense, like counting by 1s, 2s, 3s, 4, 5s, 10s, halves if you need to. Make sure whatever scale you use through the entire time. Spread the graph out. Okay, you want to use most of the available space and make sure you're consistent on both of your axes, and then you plot each data point. Okay, we haven't talked about this, but this is really great, and I'm glad you guys are looking at this right now. So a direct relationship, that means that both variables are increasing. You can see this in this line. So that's what we call a positive correlation. So correlation is the relationship between two things. So, and this one says an indirect relationship. As one variable increases, the other decreases. Okay, so but notice those are both relationships. And then a constant relationship means the change in one variable has no effect. So there's no effect that's happening due to the change in the independent variable. Okay, best fit peak line. So a peak is your highest point of data. Another thing I want to show you on this is a very symmetrical data because if I drew a line down the middle, it looks almost exactly the same on both sides. So that's actually a great set of data when you can see that it's symmetrical on both sides. Okay, let's take a look at our first practice problem. So it says the thickness of annual rings indicates what type of environmental situation was occurring at the time of a tree's development. So I'm going to show you a picture of what this means. Okay, so here is a picture of a tree. I'm going to finish reading. So as I'm reading, think about looking at this tree, the rings of the tree. So a thin ring usually indicates a rough period of development, okay, such as lack of water, forest fires, or insect infestation. On the other hand, a thick ring means prosperous period of development. It means like the weather was good, it had enough food or enough water, enough photosynthesis. Use the information from the data table below to create a proper scientific graph and to answer the questions. So if I'm looking at these rings, I can see right here, this is a really thick ring. So that year must have been a really great year. And the number of rings is for each year. Okay, but we can look at some of these thinner rings, like towards, those are probably rings that maybe it could have been a rough year, or even some of these out here on the outside. Okay, so that's what they are talking about in this. The more rings a tree has, the older the tree is as well. Oops, we just want to get rid of the picture. Hold on. There we go. Okay. So first, let's start off by finding what's our dependent independent variable, and then we're going to go graph, and then we're going to come back and answer the rest of the questions. So it says, what is the dependent variable? Well, we know that based on this, the rings of the tree are about what's occurring at the time of the development. So the thickness of the rings is going to be your dependent. Your independent is going to be time. We talked about that in math class, that time is always independent. Okay, now let's take a look at how we would graph this. Okay, so first thing first, let's label our x and y-axis. Our x is on the horizontal, our y. And I know Ms. Wallace also likes you to label your IV and your DV. Okay, so then we also need to label what they are. So this is going to be years down here, and then we are going to have the thickness of the rings. So that's going to be on, okay. So let's look at what we would count these years by. I see it's going 10, 20, 30, 35, 50, 60. So I'm going to come over here and count. I think I can skip count by tens. So it's every 5 really. 10, 20, 30. Yeah, that'll work. Okay, so we have 0 here. So then we're going to have 10. Oh, whoops, put it on the wrong side. Sorry, didn't mean to do that. This side. So we could do 0 and then 10, skip count 20, skip count 30. Ms. Wallace might even want this spread out even more because I think you could do it. Here, let's try it even a little further. If I did 0 and then we did every 3, 10. Actually, I wouldn't do 3 because you need the 5. You need that middle. So I would do it every 4. 0, 1, 2, 3, 4, 10. 1, 2, 3, 4, 20. 1, 2, 3, 4, 40, 30. Whoops, we're gonna skip number. 3, 4, 40. 50. Yeah, plenty. There we go. 3, 4, 60. 1, 2, 70, and then 1, 2, 3, 4. That would be 80. Okay, please write neater than I am. That was not neat. Okay, and then on your thickness, you can see it's 20, 24, 36. The highest is 46. So I'm thinking I'm going to count how many spaces we have. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Okay, so maybe counting by fives and skipping. So I'm going to say 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. So 51 will just be a little bit off. Okay, so if we graph these, remember we have two different ones. So I'm going to put Forest A is going to be in red for me. And then I will do Forest B in green. So remember to make your key for Miss Wallace, make it nicer than mine. Okay, so we have at 10 years, 20. So 10 is 20. 20 years was 24. 30 years was exactly 30. 1, 2, 3, 4, so here. 40 years was, there wasn't a 40 years, there's a 35 years, so that's about half, that's halfway in the middle. That was 34, so that's here. 50 was 41, so I'm trying to connect those two. They're right about there. And then 60 was at 46. So right about there. So it almost makes a pretty nice straight line. Almost. Okay, and then we have our green. Let me switch to green. Forest B was 10 was at 24. And 20 was at 28. This one's a little easier because now I know where the line exactly is. 35, 38, so it's about there. 45, and 51, which we're just going to put right there. Okay. So those are our dots. We can see the trend in the data. So now let's answer these questions on the next slide. So make sure you're looking at your graph while you're answering these. Okay, so our first question after we've already answered 1 and 2, number 3, what was the average thickness for Forest A? So Forest A is my red, and if I'm looking at 40 years, here's 40 years. If I look, my line should be like right about there. So I would say about 35, 36 would be a good estimate. Remember, this is an estimate, 35 to 36 years. What is it called when you make predictions within the given data? So that's that inter, because it's in the data. Interpolation. Okay. What was the mean thickness of annual rings for all trees found in Forest B? So this is when you're going to have to get your calculator and add those up and divide by how many there are. So let's do that real quick. So I got 221 when I added all up at Forest B, and then we're going to divide that by 6 because that's how many data points we have. And it's 36 and 8/10 is what we would round that to, and that is in millimeters. Okay, and it's not squared because we're not talking about area. Okay, based on the data shown, what can be concluded about the comparative health of Forest A and Forest B? Well, we can clearly see that Forest B had thicker rings. So you could say something about that Forest B had thicker rings from the beginning, so Forest B must be had good weather conditions, good conditions for the tree to grow. Okay, and what type of relationship? Constant, direct, or indirect? Okay, so this is a direct relationship because both as the trees got older, the rings got greater. So that's something you would write, is as the trees grew older, the thickness of their rings grew as well. Okay, so I hope that helped you with problem 1. Let's move on to problem 2. Okay, let's look at our second problem. So it says clams were placed into various temperatures of water. Use the information in the data table below to create a proper scientific graph and to answer the corresponding questions. First off, let's talk about our dependent, independent, and then we'll start our graph. So if we're looking at the development of crabs, and remember I talked about this as well in math class, that whatever's first is your x, the second is your y. So that tells you your independent and dependent. So number of clams is our dependent, because that's what we're looking at, is how many clams were able to be developed in the type of temperature of water is going to be your independent. Okay, because that's the thing that is changing. Okay, let's move on now to the graph. Okay, let's start by labeling our x and y axis. So we have our x, IV, dV as well, and so we know that this is temperature is going to be down here. And then let me move the table over a little. We're going to move it over here now. And so this other side is our y-axis, and it's our dV, whoops. So we have, and this is, oh, and you probably need to write that the temperature is in Celsius over here. And this is going to be your number of clams on the y-axis. Okay, so if I'm looking, I can see that it's counting by fives pretty much on the temperature. So I'm going to do that as well. I'm going to skip probably just about every 3, I think will be enough space. So 5, skip 3, because last time I skipped 4 and that was a lot. 15, 20, 25, 30, 35, 40, 45, 50. And so that would be 55 if we needed it. Okay, and then if I'm looking at the clam development, I mean, it goes all the way up to 140. So maybe counting by tens would be a good one for this one. And I would skip every other line. So 10, 20, 30. So notice if you skip 2 on the first one, you skip 2 every time, because you've got to maintain the same spacing. If not, your graph's going to be completely off. 60, and you might make wrong assumptions about your data based on your wrong graph. 80, oh, that didn't work. Nope, the graph is not big enough to do that. So we might actually have to count on every line. And let's erase that. That's okay. That's what happens. We try something, see if it works. I'm actually going to move this label over a little. I'm going to write number of clams over here so I have more space to write. Okay, so we're going to count every line. So this is 10, but I'm going to label it 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140. So I am counting by tens, but I'm only labeling the every other one. 150, 160, because you don't, it's going to cram all your data, 170, 180. I know we don't need to go that high, but the other counting did not work, so that's why we're doing it this way. Okay, so let's look at our data now. We have 15 is at 72, so we're going to go to 15. And we don't have to do different colors because there's only one set of data, 15, 72. So 72 is going to be a little bit in between where 70 would be and 80, so about there. And then 20 is at 92. So we're going to go to that 90, just a little bit above. 25 is at 120 exactly, so that is right there. 30 is at 140 exactly, which is right there. Did I go too far? No, that's right. 35 is at 99. Ooh, so that took like a little dip there. So 35, 99, so going, there's, trying to look for my 100 mark there. Is that it? Yeah. Okay, and then 40 is 72. So I'm seeing a trend here that's because that's what you're wanting to look for, are those trends of what is happening. 45 is at 36. So probably about right there. And then 50 was at 0. So we can kind of see here that this relationship went up and then it went down. Okay, so let's move on to answer the questions. Okay, so after 1 and 2, our question is, what is the optimum temperature for clam development? So that's going to be like, where did we see the most clams? Well, if I look at the bottom on my table, I can see it's at 30 degrees Celsius was the optimum temperature. That's when the highest amount of clams developed. It says, what is the mean number of clams per sample? Okay, so that means we are going to add all of these together and divide by how many we have. So when I added all these together, I got 631, and we are going to divide that by 1, 2, 3, 4, 5, 6, 7, 8. Yes, you do count the 0 because that's one of your numbers. And I got approximately 78 and 9/10, or you could round that to approximately 79 clams per sample. Approximately how many clams would be developing in 10 degrees? So this is where we're going to be looking at our data. Go to your 10 degrees and look at this line. Like if I drew a line, there we go. That's about where it would be. And if I go to my 10, it's going to hit there. So I would say maybe about 50 clams would be a good estimate. What is it called when you make predictions about the data not yet recorded, such as prediction we made in question 5? Okay, so it's not there. The information's not there. So that is the extrapolation because it's not on there. It's not given to you because it's extra. Okay, let's take a look at practice problem number 3. So it says Natalie sets out to run 15 kilometers. Every 30 minutes she checks her pedometer. So a pedometer tells you how many steps you've taken or how far you've gone. To determine how far she had ran, use the data below to create proper scientific graph to answer the corresponding questions. Okay, so let's first start with defining our dependent independent. So just like said earlier, time, always independent, every time. So your minutes are going to be your independent, which means the distance in kilometers is our dependent. Okay, and then we will come back and finish these questions in just a second. Okay, let's start with labeling our X. Let me move that again. It moved down a little. X and IV and our Y and our DV. So we said our minutes was going to be our independent variable, and our distance in kilometers is going to be our dependent. So we need to make sure, put that in parentheses, okay? So then obviously we're going to start with 0, 0, but then if I'm looking here at my time, I see I have 30, 60, 90. So it's counting by 30s, which is nice when it just counts for you by a certain amount. So we're just going to spread out. I'm going to spread it out again by 3. That worked really well last time. 60, 1, 2, 3. 90, 1, 2, 3. 120. 1, 2, 3, 150, 1, 2, 3, 180. Miss Wallace might want you to spread it out further, but tell her, Miss Gillum, spread it only this way because I think that's going to be enough of the graph. So then we have 6 and 8/10, 10 and 1/10, 12. I mean, those are little. So we're actually going to count by ones, but we're going to skip every one. I think we can do that. Let's see, 1, 2, 3, I'm going to do practice run 4, 5, 6, 7, 9, 10. Oh, nope, that doesn't get us where we need to get to. So I can't but count by halves. That's what I really wanted to do. So I guess we'll count by 2s to make sure we get everything. So 2, 4, 6, 8, 10, 12, 14, and we're going to finish counting even though we don't need to go any higher after 16, but we're going to finish the counting. Okay. So 0, 0, obviously, if she runs 0 minutes, she's gone 0 miles. 30 was at 6 and 8/10, so you're going to go above. So remember the halfway point would be 7, so it'll be just a little below that. And then 60 is 10 and 1/10. So we're gonna go to the 10 and we're just gonna be a little bit above there. 90 is exactly 12, so that's exactly gonna be where those two lines cross. 120 is at 13 and 3/10, so we have to remember that 13 is that middle number here, so it's gotta be a little higher than that. And then 150 is exactly at 15, and that's gonna be in between 14 and 16, so there's 14, so there would be 16. So we can see, you know, this graph here is kind of like taking off, okay? So now let's answer some of these questions that we have left. So it says, how many kilometers had Natalie run after 40 minutes? So if you look at your graph and you go straight up about where 40 minutes would be, what would you say that time would be? So looking at my graph, I would say, you could say 8 kilometers, I would say is a good estimate of where she would be, is about 8 kilometers. What was Natalie's average speed over the course of her run? Use the formula, speed is distance divided by time. Okay, over her entire run. So she ran 15 kilometers in 150 minutes. Okay, and so if we divide that, you will get, so if you did that, you'll notice you'll get 1/10 of a kilometer per minute, which doesn't seem like a lot, but a kilometer for each minute, that's a pretty good, so that's a unit rate right there that we've been working on in class as well. Okay, let's finish up our last problems. Okay, practice number 4 just says to match the story with the graph on the left. Okay, so it's looking at comparing the distance of a car is from home. Okay, so just a helpful hint, when the car is here, this is the car being at home, okay? I had just left home when I realized I had forgotten my books, so I went back to pick them up. So if I look at all these graphs, which graph shows the car going back home? D is the only one that shows the car going, leaving, and then turning around, and then getting the books, and then leaving again. So D is the only possible choice for number 1. The battery on my electric car started to run down. Okay? So, let's come back to that one. I'm not sure, actually. Things went fine until I had a flat tire. So think about that. So if you have a flat tire, so you were driving just fine, flat tire means you're not moving. Your car's on, you're having to fix the flat tire, and then you fix your flat tire and you can drive again. So that would be B. I started out calmly but sped up when I realized I was going to be late. Okay, so started out calmly, zoom, sped up, because that you're going faster, going up. Okay, so that is going to be A, and then, yes, okay, that makes sense for C, okay? The car was going just fine, and then it started to run down, so you're gonna slowly stop, so that would be C. Okay, practice problem number 5. The pie chart shows the approximate percentage teenagers spend doing various activities in a day. Use the information in the pie chart to answer the questions below. What percent of the day is spent watching TV? Well, find TV and you can see, oh, it's 13%. How many hours are spent sleeping? That one's easy, right there, 33%. What activity takes up the least amount of time? So that means the lowest. Well, right here, this 4% of studying. Wish it was higher. What activity takes up a quarter? Remember we talked about quarters, money. Okay, so you're looking for, like, if I broke this into quarters, this would be quarters. So that's your school. School takes up a quarter of your time. What 2 activities take up 50% of the day? So that means if you added these 2 together, it would take up 50% of the day. Well, you can see kind of where I drew my line. let me draw right here. If you draw a line here, you can see the phone and sleep take up about 50% of the day. So sleep and phone. That's probably even more now. Since this is old, I am sure that is totally not correct anymore. What two activities take up 25% of the day? So you got to find two activities that add up to 25. So you can automatically eliminate school and sleep. So if I added TV and eat, that wouldn't be 25. Oh, phone and eat add up to 25. So phone and eating, because 8 plus 17 is 25%. Okay, last problem. Okay, so in problem 6, we're looking at the quantity demanded versus the price per bushel. So a bushel is like a bush, like a bush in a yard. That's a bushel. So if I'm looking at this, the first thing it wants to know is what is the dependent. I know in math class I said 99% of the time it's money, but for this scenario, it actually isn't. So you always want to look at your y-axis, and it is the quantity of the demand. Quantity demanded, okay? And so what quantity demanded means is based on the price, how many people are buying it. So like for $1, there is about a quantity of 50 is demanded. For $2, an 80, okay? So as you can see, the more expensive the bushel, the lower the demand is. People don't want to pay as much. Does the price per bushel always increase with demand? No, it doesn't, because you can see that when the demand is lower, the price is higher. Okay, so I would say no. Oh, whoops, wrong. Put that in the wrong spot. No, the price per bushel does not always increase with the demand. Okay, because it increases here, okay, but over here the prices go up and the demand went down. So that's why I'm saying no. What is the quantity demanded when the price is $5? So if we're looking right here, right in between 0 and 20, that would be 10. Don't know what I was writing there. And then what is the price per bushel when the quantity is 80? So if the quantity is 80, the price per bushel is $2. So the more bushels they have, the cheaper, overall, the cheaper the price. Okay, if you have any questions, let me know. If you think you disagree with anything I did, please let me know, because this is the first time I've actually worked through this. So there is a chance that Ms. Gillum could have made a mistake, but hopefully I didn't. But I will see you guys on Wednesday. Enjoy your 2 days of having remote learning. Bye, guys.